get the idea from there of what's happening. But the point to make here is all of these files, so almost the entire program, the part that's not done in this orange, by the end of this orange band is like, we generate a small amount of procedurally generated code that we then mix back in, right? That hasn't happened yet. But all of the program text that's actually in files happens here, and it goes through the lexer and through the parser and is done being parsed in 61 milliseconds. And actually, remember, this number is inflated because it's got all this timing in here, where if you zoom in here really far, I've got timing gates around all this stuff, and that takes time itself, right? So on my laptop, for example, not running with profiling, this is under 50 milliseconds, right? In under 1/20th of a second, we've lexed and parsed this entire program. And that's basically a linear operation because you don't need to cross-reference anything with anything else. So this part will just scale linearly. So a program 10 times as big, right, if you have the profiling hooks on, will be under 600 milliseconds, or around 600 milliseconds, right? And without profiling, will be under a half a second. So sometimes people think, lexing and parsing are hard or whatever. They're not really hard, right? We did 30,000 lines in 60 milliseconds. It's not hard. Now, the other thing to know about this is the absolute maximum number of how fast we can be. So recall, all of this is happening in one thread, right? This is all serialized. However, parsing is almost completely embarrassingly parallel. This is not a language like C or C++, where we need to wait to know what some symbols mean in order to parse. Every single one of these orange blocks down here can be parsed independently, which means if you have a job system, you can farm these out to a bunch of jobs and parallelize things, right, to the extent of however many processors you have. Which is why I was saying it should be easy to get at least a 3 or 4 times multiple on these numbers that I'm showing. Probably you can get a lot more than that, but 3 to 4 times is a little bit of a pessimistic estimate that, like, oh, we're going to be waiting on other threads sometimes, or just have contention for resources somehow, right? But let me zoom in here a little more because it's fun, right? So if we're going to load a file like main, let's go into main, right? So for here, this lexer set input from file, this is the time it takes to actually load the file off the disk. It's an SSD, so it's not that long. It takes about 90 microseconds. This is maybe time that I didn't profile yet because it's pre-lexer. And then, the lexer starts feeding tokens to the parser, and each of these is a top-level statement. So I can see top-level statements, and I can map these. So first of all, I have the location in the source code where this happens, right? Like line 1053 of parser.cpp, but I can map those back to, or I can provide more information if I want, right? In the same way that I'm providing more information here, I'm in this zone load file of profiling, but I supplied the name of the file. I also, I have an ifdef in the compiler to actually tell me which top-level declaration each of these is. I have it turned off right now because, it slows things down a little bit more if you do that. But it's tremendously useful if you're looking at the thing and you're like, okay, most of these are small, but like, this one's pretty big. Which one is that? What file and line am I compiling here? You can easily add that in there. This is a very useful profiling tool, right? While we're parsing this particular top-level declaration, we're making atoms in the atom table. We're reserving memory in our dynamic array, right? That took 77 nanoseconds of 232 clocks, right? You can think down at the level of tens or hundreds of clocks, which is very, very, very useful. If you're a serious low-level programmer, this kind of thing is kind of indispensable, really. Someone's asking, oh, the formatting here is a little goofy right now. This thing that I'm using is just today a super hot build that they gave me where you can scale up the fonts, which I thought would be good just for streaming. Because it's the first day they've had this capability, sometimes fonts get a little mashed together, right? Because, it just hasn't been tweaked yet. So, oh, someone asked, what do the colors mean? Those colors are set by me. So I set colors by sort of what module roughly we're in. So gray is like system, and then green is, I forget exactly. Green is supposed to be like semantics, but maybe I set the color wrong for perform loads. Orange is lexing and parsing, right? Blue, or sorry, no, yeah, green is semantics. Blue is bytecode generation. So between all these green blocks, so here I'm figuring out what types a bunch of stuff is. Oh, and then I'm sending messages back, because remember we have this message loop where you tell the user program what types everything are. So I figure out the type, I send the message back to the user program, then I build the bytecode. So we're done. Let me reemphasize this for a second. Okay, so this is the almost 3 seconds that it took. How long did that run take? 2.0 something seconds. 2.29, right. So LLVM itself is 2.0 something, and then we run the linker after that, which takes an extra 0.3 seconds, right? So here we're running the linker. Here LLVM is chewing on what we gave it. Here we give LLVM all that stuff. Maybe this part could go faster, I'm not sure. But sort of this part, while we're using the LLVM backend, there isn't a lot of latitude, I don't think. There might be, though. Who knows? But I don't think it's an order of magnitude, is what I'm saying. But the part that is doing all the advanced features of the compiler, the part that like really determines what the language is, right, and how well it works. And I don't mean to slight, so LLVM has lots of advanced features in terms of optimization. But when I say advanced features of the compiler, I mean like semantic features like the polymorphism, and the operator overloading and the metaprogramming, all that event loop stuff. Every demo that I've showed this whole time of every feature of the compiler is happening, and it's all happening in this first 260, 270 milliseconds, right? By the time we get here, we're completely done with this 300,000 line program, right? And all of this is happening on one thread, and all of it is parallelizable, right? So all of this will get chunked up into, many blocks that are running in parallel, and this amount of time should go way down. We'll try to get the LLVM time down, but we're not sure how much we can get that down. But we'll have an alternative backend that'll go really fast, and I'll talk about that at the end. Are there any questions about what we're looking at here? These pictures are just really cool, and they're great for understanding the program. Oh, bright purple is polymorphism. So, if you zoom out, you can see it doesn't really take that much time on the whole, but as I zoom in, you can see like, okay, here's some files that are making heavy use of polymorphic procedures. Unlike C++ templates, which take forever, these are very fast, right? Let me look for a particularly long one. Like here's a kind of a long one. Let's zoom down there. So we polymorphed something. It took a lot of clocks. It took 170,000 clocks, but that was 57 microseconds, right? We generated a new version of a procedure. If I put some more debugging info in, I could tell exactly what procedure that is. I can also do some stuff, so I can get a more traditional profiler view. If I right-click on this and say Profile Zone over here, you'll see who takes how much time. And, like I said, LLVM is most of the time. Type inference takes 50 milliseconds out of this whole thing. Building bytecode takes 17 milliseconds. Polymorphism, all polymorphism in the whole program takes 15 milliseconds. Our low-level array thing takes 11 milliseconds, and that's because we add a lot of elements to arrays. Note that we added 126,000 things to arrays. So I'm going to try and see if I can get that down. Like the parser uses arrays in places where maybe we could get around it and stuff. What else is interesting? The sort of pipe of, during one of the demos or at some time, I talked about the pipe that things go through in the compiler, about the run pipe and the build pipe and the size pipe, and those are all here. So a lot of things go through these pipes, but they go through in big batches. It doesn't take too much time, a few milliseconds per pipe on the scale of the whole program. Here's overhead from telemetry, which is very small. Questions about what we're looking at. Bytecode builder is spelled wrong? What? Oh, there's a typo in bytecode builder. That's great. It's because I typed that by hand. You can, if you want, telemetry will look up the name of a thing for you, but that one's typed by hand, and I typoed it Okay. So anyway, I think that's the main thing that I wanted to show is that the compiler itself, the front end, okay, the front end runs really fast. It's done with profiling overhead. It's done with this particular program in 275 milliseconds, give or take. That is extremely parallelizable. But also, right, the thing that I was saying is in the short to medium term, I would like a faster backend than either the C backend or the LLVM backend, which both take about the same amount of time. Now, again, that's kind of nutballs, right, that I can output. So let me show you the output of the C backend, right? Oh, I rebooted, so I don't have my Emacs up. Let me get Emacs. So when you compile using the C backend, why is my font so small? Emacs must be scaling to the display size. Oh, sorry, guys. Anyway, this will help the file look big, so it's going to be fine. Right, when you compile to C, it outputs a C program full of stuff, and it's just a ton of here's the type info for the program, and there's that in an array, and eventually, well, there's some data structures, and eventually we get to real code. Let's go to like line 40,000. Now we've got some actual code, which I don't try indenting nicely or whatever. This is old style or kind of old style C compatible, so I don't use really that much in the way of advanced features, so that it'll run on a wide variety of compilers. And I really I don't indent much or anything because I'm trying to optimize for output speed. However, I'm not optimizing that hard for output speed because we're doing all this with fprintf over and over, and it takes like 0.2 seconds to generate this file. This file is 210,000 lines long, right? So it is faster for Visual Studio for me to write out a 210,000 line text file, and then faster for Visual Studio to read that text file, do all this redundant parsing and lexing like the stuff I just did, but on 10 times as much stuff, or 8 times as much stuff, and then generate an output file than it is for LLVM's API to generate a file without doing any of that overhead. So again, we're not experts at using LLVM yet, so there may be things we can do that are faster, but we've sort of been trying. We've sort of been trying to make it fast. This is to say that neither of those routes is going to be particularly fast. Yeah, so this is 210,000 line C file that we just spit out, compile it, whatever, right? Okay. So like I'm saying, though, a much faster backend, in theory, would just take our bytecode instructions, convert them directly to x64 instructions, write out an executable with minimal fuss, and be done. And so that would take time, but I don't think it would take more time than building the bytecode in the first place. And as you can see, building the bytecode is not that much time on here. In fact, if I zoom into some of this stuff that looks blue, this is actually the blue of you're not zoomed in. Right, the bytecode blue is not taking up most of that time. So these little blue blocks in between the green blocks are building bytecode. It's very fast, right? The green blocks are all the advanced features. Generating x64 instructions should be even faster than this. So it should be a really tiny amount of time. Like it should take up this red maybe or something. I don't know. Anyway, this is all just to say the medium-term plan is to provide a new option for an x64 backend, which I've started on right now, that outputs x64 assembly directly. When we get that working, which hopefully won't be too hard because we're going to use a very limited subset of instructions, when we get that working, then I'll transition to writing an output object file directly so that we don't even go through the assembler, right? So by the time I'm writing binary x64 instructions into an output object file, that should go pretty fast. Now, the annoying thing about that is that won't have debugging information initially. And what's great about the LLVM backend is it's doing all this debugging info work for us. So we're then going to see how hard it is to try and put debugging information in and whatnot. But that is the plan for the medium term, is to get everything. Like, let's give ourselves some slack and say, Our front end should be done in 300 milliseconds, right? For whenever this is done. And then, we still might rely on this linker for now. So let's say that takes another 300 milliseconds. So like, until we get rid of the linker, we'll be at 600 milliseconds or under, and still without parallelizing anything, right? And then by parallelizing, we should be able to cut that down drastically. And then by getting rid of the linker, we should be able to cut it down even more drastically. Rather than getting rid of the linker, it might be possible to sort of isolate the symbols that go out, or generate all position-independent code, or do some things to try to minimize the amount of work that the linker does, which will be another option that we pursue. I think that I've said everything I wanted to say. Yeah. Long-term. So that's the medium-term plan. Medium-term plan, parallelize the front end, generate an x64 backend, right? In the longer term, I don't know what's going to happen because, so like I'm saying, LLVM is great. It does a lot of work for us. It generates good debug info. It generates good optimized code. However, if everything I'm saying is right and not a bunch of BS, and if we can compile a big program in a fraction of a second, or a medium-sized program in a fraction of a second, and a big program in single-digit seconds, right? Then to transition back and forth between something that fast and something that's an order of magnitude slower, or 1.5 orders of magnitude slower, is going to be uncomfortable. And we'll cross that bridge when we come to it, but we might not be able to use LLVM in the very long term as our final backend, depending on how fast we can get it to go. But yeah, I think until then, and when I say long term, I mean years from now, right? So for the next couple of years at least, our serious backend will be LLVM based. It's doing a lot of work for us. It's had a lot of good effort put into it, and I'm very happy that we're able to leverage that effort. But there are drawbacks, and I don't want to. I don't want to be blind to the drawbacks, and I want to try to take them into account in my planning here. Let's take questions. Does anybody have questions? Someone's asking, have I tried to write degenerate polymorphic code like crazy sauce, template metaprogrammed ray tracer stuff to see what the upper bounds of parsing polymorphic code looks like? No, I haven't yet. I'm, for the most part, trying to do a game in the style of games that I like to do. I'm not sure what, I mean, you're probably thinking of a specific example when you think about the ray tracer. I'm not familiar with that kind of example, so I don't know what their usage looks like. I will say, though, that parsing polymorphic code isn't a problem. We only ever parse things once. So here, polymorphic procedures are being parsed in this orange band here, along with everything else, right? It all just happens at the same time. These purple things, which are the specialization of the polymorphic procedure to whatever you're trying to do, don't reparse. It's not like a textual substitution. It's a semantic substitution where we just define some variables, right? So this is all data structure copies and whatever, and we skip all that overhead of parsing, right? We're copying the syntax tree of the procedure. And, you know, really, we maybe shouldn't even have to do that in the long term. It's just that the way that the compiler works right now is I store the type on the node of the syntax tree, and so when you want to change the types of things, you have to copy the tree. And that's where polymorphism spends most of its time, but there absolutely is not any reparsing. Do compiler developers have some other goal that makes it so they're slow? You know, I don't know, man. I mean, some compilers are kind of fast, like the Go compiler is kind of fast, although it got slower when they rewrote it in Go from C++, which is a little concerning, but they're working on that. It didn't still get nearly as slow as like a C++ compiler or whatever. I don't know why C++ compilers are so slow. I mean, I know part of why they're slow, which is just, they're re-dealing with the same include files many times. But they're slower than that. And so I don't know what's going on, actually. I don't know what's going on with most compilers in the world. Maybe they're using parser tools to generate their code, and they think that those tools, or generate their lexing and parsing code, and they think that those tools are supposed to generate fast code, but really it's not that fast. I don't know, right? All I can tell you is, dude, I'm parsing 33,000 lines in 60 milliseconds, 50 milliseconds if you take out the profiling overhead. And that's as slow as it will ever possibly go, right? The more we optimize the parsers, and the more that we parallelize things, this number will only go down. So I honestly don't think there's any reasonable excuse for how slow many compilers are. Now, a lot of the slowness, of some systems doesn't happen in parsing, right? It happens out here in like semantics, which is the green blocks here. So for example, the green blocks here include such things as looking up identifiers to figure out what type they are. Or, operator overloading, like if you use a plus, and it's on a vector, like what operator is that? Now, some languages like Swift do some sort of like crazy tree search to try and resolve overloads and stuff. We don't do that. This language is designed so that kind of stuff never happens. So I expect, like on Swift, their parser probably maybe isn't terrible, I don't know. But they probably spend a lot of time in their equivalent of the green blocks here, like a lot of time. But it's important to me in language design to design something that is compilable very quickly. And that's one of the things I've been trying to do over this past while that I've been working on this stuff. Any timeline on alpha beta? No, I don't have a timeline yet. I would like to get this out to people as soon as it's done, right? But, being done, I have a reasonable bar for being done. It's not ready for public consumption yet, in my opinion. When that'll be, I'm not completely sure. Hopefully less than a year. I was originally saying by the end of 2016. I'm not sure if we're going to make that. It's the usual thing where the further you get into a schedule, the more you start running into things that you did not foresee. So, and it's not really development problems or anything. It's just like, oh yeah, I want to do this and I want to do that and I want this to be at a certain quality bar. So I hadn't been thinking before about parallelizing the parser, but now I'm like, oh, that would be fun. We should do it. So yeah. Someone is asking, what was the decision on function parameter semantics? I don't know what decision you're referring to, unfortunately. What do I think about OpenGL error handling? I think it's terrible. But mostly because of error messages. Like if something goes wrong in OpenGL, it's very hard to figure out what it was. On-topic questions only, please. OpenGL in the vague is off-topic. Have I thought about doing an incremental build by caching the LLVM output by function, only rebuild the functions that have newer checksums? I've thought about that a very small amount. The thing is, if we can do a non-incremental build in under a second, who cares about an incremental build? Why introduce that complexity into your system, right? Now we'll have to see if I can actually meet that goal that I'm talking about, right? But if, like, an incremental build in Visual Studio, even for the witness, even for a small change, takes many seconds. So if my speed target is that many seconds is unacceptable, then I'm going to do things differently than how systems have previously done them. So yeah. Does LLVM do anything in parallel? I don't know. And furthermore, I don't know if we're able to turn on anything in parallel. There could be threads being launched behind our back because if I don't put telemetry instrumentation into a thread, we won't see it on this list. So LLVM could be launching threads that we don't are not paying attention to, for all I know. I'm not sure. Oh, James Woodman's also asking about incremental recompile. Example, built-in GUI sliders for all floating point literals. I mean, I don't know. Like, if the compiler is really as fast as I'm going to say it's going to be, then, you know, we could start looking at something like that. Like, I was actually thinking, instead of doing, like, classical recompilation, one thing that seems like it would be pretty easy would be to compile each file into a separate DLL, and then just dynamically reload an individual DLL. You know, if you've seen Handmade Hero, Casey does that. And, well, I don't know if he does it as many different DLLs. I think he maybe just does one main one. But the point is, you know, if you have some point during your runtime that you know is safe and is not going to get reloaded, then it's actually pretty simple to swap out DLLs. And we don't have to do any weird, grody, you know, system-dependent work like maybe Visual Studio people did for their incremental build. So it's something that I've toyed with. It's just, I don't want to rely on the idea of incremental builds to be fast. I think a full build should be fast. I think there's no reason a full build should not be fast unless you're working very hard to generate optimal code. So if you just want to build and have a functioning program, it should be very, very, very fast. Faster than any compiler that you know of. And I think maybe that hasn't happened just because, you know, general programmers are not as hardcore about having to write fast code as like game people are, right? There's very few people like game people, and probably rocketry and automotive people care about how fast things run, and almost no other programmers in the world really care about how fast things run anymore. And so I think maybe some skills have been lost or just not ever gotten by new generations of programmers. So, or maybe they just buy into the paradigm, right? If you buy into this idea like, oh, C++ is fine and RAII doesn't slow down your program, or if you buy into, you know, the D thing about like, oh, certain things just get allocated on the heap all the time. That's fine. It's not going to slow you down. It does, right? It does. And that has a real world impact on the user, right? How long are people going to spend waiting for your thing to build? So this is all just to say we're going to be working hard to make it go fast. And the fact that I've said this publicly, that we should be able to build this program in well under 1 second, means that now I have to stick to it, or people will come say to me, hey, what about that promise you made, huh? So yeah, under 1 second. Can I just run the bytecode directly in a VM like Java as a quick debug development mode? We already can do that. And yes, I could. But I think it's better to run native code because it's going to be a lot faster. It should be a multiple faster than running bytecode. But yes, like I said, after this, you know, 275 milliseconds or whatever, we're ready to run the program. And we could just launch a bytecode interpreter and run it at that time. And if you haven't seen that in earlier demos, just go back on YouTube to some of the earlier demos, because we've done a fair amount of that, and it's pretty fun sometimes. I don't parse the queue in Twitch. I just look at things aimed at me. Have I thought about write time editor? Someone's asking about editor stuff. I'm not caring about editor stuff yet. Have I tried something like LCC or TCC? I have not yet. If I thought that optimizing the C backend was our fastest way to a faster backend, I would look into that. But the thing is that, you know, if I go into, oh, I don't have it here. Let's run one of these with C output. So I'm going to go here, and I'm going to change to backend C, and I'm going to recompile. All right. So we now should have a new, we have a new thing over here. This is with the C backend, so it's a little shorter than the telemetry one. So here, this 190 milliseconds here is us outputting that C file to the backend. And we spent, I don't think I logged fprintf explicitly, but we're spending most of our time in fprintf in here, right? So I could try to optimize that, but we're still probably going to spend like 100 milliseconds or 80 milliseconds outputting C code, which is longer than the entire time that I want to spend on this before the compiler even gets to it, right? So when I say the rest of our pipeline in terms of getting the back end out should be fast, I'm not talking this fast. I'm talking like maybe this sliver here where it's black under the blue, like maybe we should be done by then and have an executable, right? That's what I'm aiming for. And so even if the C compiler is 3 times as fast as this one, that's only going to shrink this gray bar down to here, right? Which is still a multiple of 3 or something over our front end time. So I don't think that that is the fastest route. And plus, I don't want to introduce another dependency. I don't want to tell people, well, you should have LCC on your system, right? But if it's like an order of magnitude faster or something, then that starts to be worthwhile. And so, maybe that's a thing. How will graphic library implementation work? I don't know what you mean. We'll have graphics libraries like anybody does. I will open source some kind of a game in this language. It's not going to be the Witness because the Witness is huge and I would like a break from working on it. So it'll be something else, like possibly this thing that I started showing today. Have we been in touch with any of the LLVM developers? Not that I know of. Joshua might have been that I don't know of, but it's possible that someone on the LLVM team could help us reduce the amount of time that we spend. But I'm not totally optimistic about it because, like Clang would be motivated to do that. And again, when we switch to Clang, right, so we're outputting the C backend and we're using our compile with Clang procedure. Clang is really a lot slower than either of the other options. They're like over double the time, right? And as far as I know, we're O0 and I don't know what else you would pass to Clang to make it fast besides -0. Maybe there's some other things. But it's just to say that our LLVM handling, there's no proof that Clang's feeding of LLVM is any faster than ours. Maybe it is. And maybe the other time is being spent in Clang's parser or something, right? I don't know. But a lot of time is being spent somewhere. This is, by the way, this is an official Clang binary for Windows that I downloaded from them. I didn't compile it myself, so I'm trusting that they compiled it with good options, right, to have the compiler be running fast code. Who knows? Any plans to have a backend which can write JavaScript? I will not touch such a thing with a 10-foot pole, but I'm sure somebody will. Like an asm.js outputter or something. You can do that kind of thing at user level, remember, right? You don't need the compiler to tell you what the program is because you get the syntax tree of the program yourself and you can run code on that. So you can just write a thing that converts the syntax tree to whatever, asm.js or whatever. We could make it a little easier by giving you access to the bytecode as well, which would be kind of trivial, I think. And we might do that at some point. The bytecode's still fluctuating a little bit, so it's a little bit annoying to change an API to it all the time. But at some point when it settles down, we could export bytecode as well. And then it would be pretty trivial to write such a backend. So that would be cool. It's just, I don't like anything about web languages and will not participate in that. How many people are working on this now? Just me and Joshua. Is the speed per line of code linear, or will it get relatively faster or slower the more lines of code that you have? Well, again, it depends. Stuff like the parser is going to be more or less completely linear. So once we get over into like type inference and stuff, that's super linear because, you know, namespaces get bigger and what else? Well, you know, if you're going to resolve overloads, the number of possible overloads maybe grows, or the number of scopes deep that you are might grow with the program. But I don't think this is very much bigger than linear, right? I think it's, you know, I don't know. I mean, you know, you use hash tables to do symbol lookup, and that's the most nonlinear thing normally, right? So I think this can be mostly linear for all intents and purposes, unless we run into some kind of very constraint. Like if we start using too much memory and we have to start doing crazy things to keep memory usage down, you know, that might get harder. But so I think the green stuff is maybe the most nonlinear thing, which is a little bit, you know, it's already the majority of what, I don't count this green one, sorry. But this green stuff from here to the right, but I doubt it'll be very nonlinear. And then everything else, like the blue in here and the purple and all this stuff, is completely linear, completely. Will there be options to turn off certain language features? Yes, you can turn off stuff like array bounds checking, right, which would be a little slower by inserting extra instructions and whatnot. I was going to add a thing to turn off messaging, but messaging doesn't take that much time right now. Like, you know, messaging takes 4 milliseconds out of this entire, you know, what did we say? 275 milliseconds. So messaging is like 2% of the runtime. So you could save 2%, or 2% of the compile time. You could save 2% if you turn messaging off. Or maybe more because you've got the guy on the other end. But, you know, it wasn't worth the effort for now. We'll see what's worth doing, right? For now, by far, the next biggest improvement in times, I've already done a pass on all this stuff to get it faster. So before a couple weeks ago, this 55, it was 65 last run, but this 55 milliseconds now was double that at least. Actually, all of this was double, right? So the whole front end time was like 650 milliseconds, and now we've got it down to 275. So in a couple weeks, I was able to get all the low-hanging fruit and more than double the speed of the compiler. There's still single-threaded optimizations like that that can be done, surely. So this could probably be reduced substantially again, but then parallelizing it is probably easier. So there is that. Oh, someone's saying D compiles even faster than Go? That's cool. But I was talking about, when I was talking about the heap allocation thing, I was talking about runtime. But it's good to know that D compiles very quickly. Maybe I should use that as my speed to beat. Like how fast does D compile a 30,000 line program, for example? Plans on building profiling tools into the language. If you look through earlier demos, you'll see some profiling tools that I was able to actually build at user level. So a lot of things will probably be like that. There'll be user level libraries for instrumenting your code. James is saying, for the compile-edit debug cycle, it seems like it could be helpful to skip traditional linking and have the code generator write directly into the address space of the process being debugged. Wow, that would be crazy. I don't know if we need to do that, because loading DLLs is not that slow. Which is so actually we can look at how slow loading DLLs is because we do it here. These red blocks here, I don't know about these. No, these are different. But these red blocks here are us loading all the DLLs for all the libraries that we use. Whoops, I didn't realize that that would zoom me out. Sorry. Is this the same? Let's go here. Let's go right back to where we were. So here we are, and you know, I don't have a zone just around these, but all of them happen in a subset of this 7 millisecond, right? So we load 1, 2, 3, 4, 5, 6, 7 or 8 DLLs in, let's call it 6 milliseconds. So it's like 1 millisecond per DLL, and these are non-trivial DLLs. Like, oh, I didn't put the names in here, but you know, there's stuff like user 32 in Windows and whatnot. So the plan of outputting a DLL and then linking it from the program should go very fast. Why static linker is so much slower, I don't know. Like maybe the process of backpatching all the non-position independent code is what's slow. Maybe linkers are just slow, but it's unbelievable to me how slow they actually are. Like if patching the code is slow, I don't understand why it's as slow as it is. It's nutty how long linkers take. I don't believe it for how much data they process. And even fast linkers, like Gold is supposed to be the fast linker, the open source one, and it's like 2 or 3 times faster than old LD, I think, last I heard. I don't know. But that's still nowhere near, like a linker should be almost instant, right? Like it should be really fast because your executable is only 10 megabytes or something. Like, and everything you're trying to do is just linear there. It's like I'm trying to put some symbols in some places, right? And so then, you know, the totally naive thing would be to go over the whole executable once for every symbol, and hopefully you don't do that. Hopefully you do something much smarter than that. That said, I've never written a linker. I don't know exactly what they do. Maybe they do some like weird dwarf virtual machine thing that's like super slow. But then we would just not do any of that, right? You don't need to do any of that to output debugging information, even if you want to output dwarf-compatible debugging information. I don't believe you need to do any of that. But even skipping anything like that, if you just had like this is my own debugger reading my own debugging format, you could be blazingly fast. And if that's the fastest thing to do, then we'll do it. I don't know. Like I said, I'm from a position of at least slight ignorance as regards linkers, but I don't believe linkers have any excuse to being slow. They have less excuse to be slow than compilers have to being slow, and I've already ranted over how I think compilers have no excuse for being as slow as they are. So there you have that. Have I tried disabling optimizations in LLVM? Yes. So this build that we're doing is, I think, with pretty much all optimizations off, except for 1 or 2 things that actually make it faster when we turn them on. But there may be more things that make it faster when we turn them on that we're not aware of. So please do not take this as a blanket negativity about LLVM's build speed, right? There could be some things that we don't know about. Now I seem to have done something bad to my zoom. I've hit some key in Windows that now makes my zoom only vertically scroll. Windows. Okay, there we go. We got zoom back. Windows is your buddy. All right. Is Joshua on Twitter? I don't know. If he is, he's probably not as obnoxious as I am. So someone's saying fast anything is good, but is this premature optimization? What happens when we come out with extended language features? Extended language features will not make this any slower, really. I mean, maybe a little bit, but we're not going to introduce anything that makes things twice as slow, I hope, right? And even twice as slow should still be blazingly fast. So I'm not worried about additional language features. The only real reason to be worried about parallelizing, for example, is that it's a little harder to deal with parallel code than not. But it's easy to back out of that. If I parallelize as an experiment and it makes it too hard to work with the compiler, I can always if-def that out, and then have the job system just be serial or whatever, and then we turn it back on later when we're ready. But no, I think, so here's the thing. If you're making a new language, people have to have a reason or multiple reasons to want to use it. They have to have multiple really good reasons to want to use it, right? And if I say, look, here I'm compiling a 300,000 line game in under a second from scratch, no incremental rebuild, none of that Visual Studio annoyance where it gets things wrong because it's incrementally rebuilding, right? That's a pretty strong, reason to use a thing, right? Then if somebody hears about that, then they're just sitting there the next day trying to compile their C++ program and it takes 15 minutes, they're going to think about that, right? It's going to be a good reason to use the language. Now, at the same time, of course, C++ is advancing, and they have a module system that they're doing that Chandler Carruth, for example, just has been tweeting about. The thing is, even if that module system ends up being perfect, right, they're still going to be taking all of this back-end time that we're taking under LLVM right now, because this is all single module compilation, right? None of this, 2 seconds that it takes to do the LLVM thing comes from any of the C++ problems ever done. It includes or templates being slow or anything. All of this is post that. So a C++ module system is still going to be at least an order of magnitude slower than the kinds of compile times that I'm aiming for, unless somebody comes out with a really amazing C++ compiler, which is hard because the language is so complicated, right? So we'll see. But yeah, I'm very optimistic. So I've also, part of this is just about what makes me happy, right? Because I'm making the language that'll make me happy to use it from day to day. And I have spent a long time waiting on compilers. And even this, I would like this to be instant as soon as I do that. I would like to have an executable immediately. And I don't. So I would like to build a backend that makes that possible, whatever that backend is. And it's about what makes me happy, and so I don't think it's premature optimization. I'll probably do it a bit at a time. I probably won't do the whole thing at once, right? I might do assembly backend first because that is the lowest hanging fruit, but then we'll still have this linker chunk around for a while, so that'll be a little bit slow, and maybe the assembler won't be as fast as we wanted, who knows? And then maybe I'll parallelize the front end, and then maybe I'll go straight to machine code, who knows? But I'm enjoying working on it, and if you're enjoying working on something and, nobody's paying me to do this, right? This is my own thing, so it's not like I have a responsibility to someone who's paying me to get certain functionality done, then I'm going to do the thing that I think is best to do. And right now I feel like it's stuff like this. At the same time, I'll be pushing forward the user program. So that user program is 33,000 lines right now. It'll get bigger over time as well. Are there plans for Linux testing and demoing? Yeah, I demoed, my very first demo of this language included a Linux demo. We haven't maintained the Linux executable since then, but it's maybe about time to go back and make that start working again. So I think maybe pretty soon we'll squeak that into another demo sometime, probably. What is the future of inline assembly? I don't know exactly. I think inline assembly is important, maybe, but maybe just intrinsics are fine, right? I don't know if intrinsics are good enough. Intrinsics are probably easier, so we'll maybe do that first, but we'll maybe do both. I don't know. Would I consider making my own linker? Yes, but really, I mean, the front end already kind of is a linker in some sense. Like when I generate bytecode here, let's zoom into that. These very small amounts of time where I generate bytecode, I actually do have to go in and patch addresses of other things in a post pass, right? I don't do that. I forget in which cases I do it. I don't do it in as many cases as a linker would, but I do it in a lot of cases. That kind of functionality is sort of there. I don't think it would be the same thing. I think it would be a separate thing if we output assembly ourselves, but yeah. I don't, I guess if we just output assembly for the DLL to do final linking on, it would probably be all position independent code. Again, that's not my area of expertise. I'm looking forward to learning about that stuff when I go and do it. Will the compiler compile your programs as a single compilation unit? Yes, that's the default right now, right? So all this stuff, when I go in here, right, all this stuff that I'm loading separate text files, but they're all being pulled into the same compiler process. This is the same thread doing all these files, right? And those guys are able to talk to each other in the same namespace without header files or whatever. So yeah, I mean, the concept of compilation unit doesn't make as much sense here as it does in C++. If you decided to make compilation